Hello guys, in this video we are going to talk about gamma function. We are going to only learn the basic of gamma function. Gamma function can be applied in many places in mathematics, but we are going to just introduce the idea. We will see that this function generalizes the factorial function, and we will only see two properties. Why we are going to see this? I think it's a little bit complicated, but when we manage to work correctly with these properties, we can just solve some integrals in a very easy way. I think it's worth wasting our time with these ideas. What are we going to need? We are going to need a little bit of integral calculus. In fact, gamma function definition is an integral. And for sure, we need to work somehow with mathematical expressions. Okay, let's start. What is the gamma function? I will try to introduce more or less easily this idea. Okay, the gamma function is an improper integral. So probably you are thinking improper what? What are we talking about? Improper integral is an integral, is a defined integral, but as you can see, there's something strange in this case. There are different types of improper integrals. We are going to focus now in the one we have on the screen. It's called improper because the interval of integration is not a finite, it's not close like 1, 2, 3, 5. It's between 0 and plus infinity. Okay, so that makes things a little bit more complicated than usual. Okay, we need to talk much more about these improper integrals. But for now, let's consider this integral, and you are going to trust me with the definition of improper integral. One thing, you can apply Barrow's rule. The key point of this type of improper integrals is that they mix limits with Barrow's rule, okay? But just consider infinity as a number just for now, okay? Let's keep going a little bit and trust me that the properties that we are going to show you, they are true, okay? So, by the way, P is strictly positive in this definition, okay? It's well defined because you can calculate this integral. And also, by the way, if you want to calculate, imagine that P has a value, 5, 2, 3, whatever you want, okay? Don't start with complicated values. If P is 2, for example, then X is 1. So X is power to 1, 2 minus 1 is 1. Or if P is 3, then this is X squared. The idea is that this integral you have here, can be solved by integration by parts. Can take time. Yeah, it's difficult. No, not much. It's just you have a polynomial times an exponential function. It can be done. Probably if it is x cubed, for example, if you have cube here, you need to apply integration by parts 3 times. So it's going to take longer than the method we are going to apply now. So keep in mind this definition, okay? The integral between 0 and plus infinity. By the way, you cannot change anything. If we are going to apply this definition in the integral, please keep in mind that it's exactly like this. Don't change like, I'm going to put a 2x in the exponent. No, please don't. Okay, just this definition. Okay, so it's well defined, it can be calculated. And what do we have here? Let's start calculating some values of this function. Let's start calculating gamma of 1. Okay, gamma of 1, that means that P is 1. In the previous definition, if P is 1, X is power to 0. And anything different from 0, power to 0, it's going to be 1. Okay? So, in this case, X disappears, and the only thing left to integrate is e power minus X differential of X. The exponential function is very easy to integrate. It's exactly the same, but be careful. In order to integrate, if you use the chain rule, then you need a negative because the derivative of the exponent is minus 1, and the derivative of the exponent is not inside the integral. And this is something we need. Okay, so then what I was saying, then I need to multiply by minus 1 here and minus outside of the integral in order to have the derivative of the exponent. So the integral of e power minus x is negative e power minus x between 0 and 1. If we replace by dx by infinity, e power minus infinity, it's 0. Remember the exponential function e power minus x. It was a decreasing function and approaches 0. at infinity. So in this case, e power minus infinity is 0. And then when we replace the x by 0, e power 0 is 1. So that is the reason the result is 1. For us, for this topic, you first need to remember that gamma of 1 is 1. Okay, keep this in mind. Okay, another important property. This property, that gamma p is p minus 1 times gamma of p minus 1, is a property that is obtained using the integration by parts method in the original integral. It's not complicated. Sorry. It can be done easily, but it's an important property, guys. It's a really important property. Combining the gamma 1 is 1, and this property, gamma of p, it's p minus 1, gamma of p minus 1, we can obtain or we can calculate several values. For example, gamma of p, imagine that p is a natural number for now. It's going to be, applying this property, p minus 1 of gamma of p minus 1, as you can see here. Okay? Perfect. What is gamma of p minus 1? I can apply again this property, exactly this property, but where or when p is p minus 1. Then this property becomes p minus 2 gamma of p minus 2. Okay? So that is what I wrote here. No, it's written in general here in the formula. And we can keep going. I mean, we apply this recurrence of gamma function property again and again and again until you have gamma of 1. Gamma of 1 is 1, so at the end you have p minus 1 times p minus 2 times p minus 3 times blah 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 till 1. So what is that? P minus 1 factorial. So, sorry guys. It's not difficult. The consequence of this recurrence of gamma function is very important. Gamma of p, it's p minus 1 factorial, when p is a natural number. Okay? So, in general, let me go further. Let's put an example. Gamma of 5. Gamma of 5, by the recurrence property, it's 4 gamma of 4. Gamma of 4, or gamma at 4, is 3 times gamma at 3. Okay? Then we apply the recurrence property on gamma at 3. It's 2 gamma at 2. So 4, 3, 2 gamma at 2. Then gamma at 2 becomes 1 gamma at 1, and gamma at 1 is 1. So at the end, gamma of 5 is 4 factorial. The idea, guys, is that you can use this. I'm not expecting you to write all these numbers in between. I expect you to give me the solution when I ask you gamma of 5, 4 factorial. Let me put more examples. Gamma of 7, 6 factorial. Okay? In general, here you have the formula. When we have natural numbers, gamma of n is n minus 1 factorial, as we saw before. Okay? So this is very important property. One more property. Remember the definition of gamma function. Okay, so we are now able to calculate this integral. The integral, for example, between 0 and plus infinity of x to the 5th power times e power minus x dx is exactly the, let me go back 5 seconds. This is the definition. Then I just changed p minus 1 by 5. So if we just keep going with this definition, as you can see here, 5 should be p minus 1. So what is the value of p in order to calculate this gamma function? If 5 is p minus 1, p is 6. Perfect. So by definition of the gamma function, this integral is gamma 6. But you know that 6 is a natural number, so gamma of 6 is 5 factorial equals 120. So probably you are thinking, so what? I understand the question, but keep in mind that if you don't know this information, and you remember what is integration by parts, if you want to calculate this integral, okay, be careful, because this means that you are going to apply integration by parts 5 times, and that is not short. It's not easy. You need to take your time to integrate that thing. If you know this property, look at the final conclusion. If I need to integrate x to the 5th power, e power minus x differential of x is this number factorial. And it's done. 1 second, and you got the final result against 10 minutes of work. Okay, so the idea is that it's a really good property. And probably you are now asking me, yeah, but I need to have exactly this integral and cannot be applied in a more general way. Yes, you're right, okay? You need to have exactly what you have in the screen. The other example, what can I change this number only? Now is 3, so this integral is gamma of 4, but gamma of 4 at 4 is 3 factorial, and it's 6. So once you see this integral exactly like this, you only need to take care of this number and factorial this number. Okay? So piece of cake. Again, we will see where this applies in a more general context. Another property. This I told you, or if I didn't tell you, I'm telling you now. Gamma is a generalization of the factorial function. It can be calculated with numbers that are not natural numbers. How are we going to do that? Exactly with the same properties we saw before. The recurrence property and this one, gamma of 1/2 equals square root of pi. So be careful, because if you want to, gamma function is you can find the values of a gamma function in a table. You can just look at in internet for gamma function and you will see tables with a lot of data. So gamma of 1/3 can be found and you can calculate it. I am going to use gamma of 1/2 equals the square root of pi because it's a really beautiful result, and also because I can apply this in the exams or in the exercises. Okay, so remember that I'm trying to avoid the use of tables because I don't want you to be looking in internet right now or during the exam just looking for some information. I want you that this could be solved easily without any other help. So I'm going to focus on gamma of 1/2 equals the square root of pi. Everything will be solved using natural numbers or this property. Let's see another exercise. And with this we finish because I think it's enough to start working with the gamma function. Recall, gamma of 7 is going to be 6 factorial. This is piece of cake because 7 is a natural number. Gamma of 9, 8 factorial. Gamma of 3/2, be careful, this is new. Gamma of 3/2 is 3/2 minus 1. 3/2 minus 1 is 1/2 of gamma of the same number. Gamma of 1/2, as the previous property told us, is square root of pi. So gamma of 3/2 is 1/2 square root of pi. Probably you are now confused, like, okay, I'm not catching the idea. Don't worry. Let's see the three next calculations, and I think you will start catching grasping the idea. Okay, so gamma of 5/2. How is this calculated? Remember that I'm only going to ask you a number divided by 2, okay? Because if not, you need a table to solve this gamma function. So gamma of 5/2. You start subtracting 2 units to the numerator. So 5 starts at 3/2. Then you keep going down until you reach 1/2. 3/2 minus 1, it's 1/2. So 3/2, 1/2, square root of pi. Gamma of 7 pi, look at the shape. You start with 7, but the first number is 2 units lower. 5, 3, 1, and everything is divided by 2. At the end, square root of pi, because at the end you end in gamma 1/2. Okay, and gamma of 9 divided by 2, okay, 7/2, 5/2, 3/2, 1/2, square root of pi. And let's just stop here. What is gamma of 11 divided by 2? You start at 9 divided by 2, 7 divided by 2, 5 divided by 2, 3 divided by 2, 1 divided by 2, times the square root of pi. Okay? So it's not difficult. Take your time to look at this and practice with some other values, and you will see that these properties are really useful in the future. Okay? So what have we seen today? Introduction, general introduction of a gamma function, only the definition and 2 properties, okay? The recurrence property and that gamma of 1/2 is a square root of pi. Also gamma of 1 is 1, okay? And then we apply these properties, the first part, in order to calculate a type of integrals, okay? With this is enough. I think it's probably you are thinking it's too much, but I guess you understood everything. You will find this helpful, for sure. Thank you for your attention, guys.